8 Mysterious Boundaries of the Universe, 2. Hello everyone. Welcome to my channel. The boundaries of the universe can be understood from different perspectives, including physics, observation range, theoretical limits, etc. In the vastness of the starry sky, we always used to think that the universe is infinite, full of endless possibilities. Under the vastness of the starry sky, we are always accustomed to think that the universe is infinite, full of endless possibilities. However, scientists have discovered that the universe is not boundless. It has limits that we have not yet touched, and these limits may determine the life and death of the universe, its fate, and even our own future. From dark matter to black holes, from quantum entanglement to the silence of extraterrestrial civilizations, from dark currents to the cessation of time on a cosmic scale, these enigmas, known as the boundaries of the universe, hide mysteries we cannot imagine. Today, we will continue the previous installment and take you to unravel the mysteries of the 8 major boundaries of the universe together. 9. Time-stopping boundary on the cosmic scale. You may have heard that when an object approaches the field of view of a black hole, time slows down more and more until it seems to have stopped from the perspective of an outside observer. That's the core concept of the time-stopping boundary we're going to talk about today. But we're going to zoom in on this phenomenon on a cosmic scale to explore those mysterious regions where time stops under extreme conditions. We know that in Einstein's theory of general relativity, gravity affects not only the shape of space, but also the passage of time. And one of the most extreme gravitational fields is a black hole. You may have heard that black holes have a mysterious event horizon, a region that acts as a demarcation line, and once you cross it, you can no longer escape the gravitational pull of the black hole. One particularly interesting phenomenon is that as an object approaches the event horizon of a black hole, time becomes slower and slower. If you stand at a distance and observe an object that is about to fall into a black hole, you will notice that time passes more and more slowly for it. The closer the object gets to the edge of the black hole, the more time becomes almost stagnant. To you, the observer, it seems that the object will never actually cross that field of view. This is known as time dilation, or rather, the relativistic cessation of time. Sounds fantastical, doesn't it? It's one of those mind-boggling but experimentally verified phenomena that relativity has given us. Well, now that we know that the gravitational pull of a black hole can stop time, the question arises, is it possible that there are similar regions or boundaries on the cosmic scale where time also stops? This question is even more mysterious. Imagine that there are regions of the entire universe, or some kind of giant structure, where time almost freezes. This sounds both terrifying and mysterious. One theory suggests that if the universe has extreme gravitational fields in certain regions, similar to the field of view effect of black holes, then time could also freeze or expand extremely near these regions. In other words, these regions might form a sort of time-stopping boundary. This is not just a tiny area of a black hole's field of view, but a phenomenon of time freezing on a cosmic scale. To discuss time-stopping boundaries in the universe, we must first understand that the relationship between gravity and time does not only exist around black holes, but that the gravitational distribution of the universe as a whole also affects the flow of time to some extent. For example, close to massive bodies of mass, e.g., galaxy clusters, supermassive black holes, time passes more slowly than away from them. So where in the universe could a situation be so extreme that time almost stops? Here are some possible candidates. 1. Black hole clusters. In the universe, there are often supermassive black holes at the centers of galaxies, such as the one at the center of our Milky Way galaxy, which is the mass of more than 4 million suns. If there are clusters of huge numbers of black holes in the core regions of certain galaxy clusters, their gravitational fields may affect the flow of time around them. Close to these regions, the time dilation effect may become extremely significant and even form boundaries similar to the stopping of time. 2. Gravity wells. In the large-scale structure of the universe, in the structure of the cosmic web, there are structures called dark matter filaments, which act as giant gravitational networks connecting galaxies and clusters of galaxies. Between these structures, there are places where the gravitational pull is so strong that they form so-called gravitational wells. Theoretically, if these gravitational wells were deep enough, time might also expand significantly. 3. Extreme regions of cosmic expansion. In addition to gravity, the expansion of the universe itself also affects the passage of time. During the accelerated expansion of the universe, distant regions move away from us at increasing speeds, even reaching above the speed of light. In these regions, the passage of time almost stops for us because no information can be transmitted from these regions to us anymore. Such regions can also be thought of as boundaries where time stops. If there really is some kind of time-stopping boundary in the universe, perhaps we can get a glimpse of the early state of the universe. Imagine if you were standing at the edge of an extreme gravitational field and observed that time was stopped. Then looking out from there, you would see the world as a snapshot of the past. It would be like preserving a piece of the universe under extreme conditions, forever at that point in time. For example, a scientist named John Archibald Wheeler developed a theory about the field of view of black holes. He said that information about objects falling into black holes is actually recorded on the surface of the black hole, i.e., at the field of view, and from the outside world. This information exists forever at that point in time. Thus, in a sense, this boundary preserves the static state of the information. On a cosmic scale, if there are similar, time-frozen regions, then perhaps these places are also like the memory cards of the universe, preserving information that may never be accessible to us because it is trapped at the boundary where time stops. You may be wondering how scientists are able to get the information they need from the universe. You may wonder how scientists can investigate such a concept. They can't actually fly to these time-stopping places and measure them, so they rely on a combination of theoretical calculations and cosmic observations. First, scientists use Einstein's equations of general relativity to calculate the effect of time dilation in extreme gravitational fields. These calculations are able to predict how the passage of time changes as an object approaches a black hole or other extreme gravitational field. Meanwhile, scientists are also using observations of the cosmic microwave background radiation, CMB, to infer whether similar extremes exist in the universe. In addition, researchers are also looking for the gravitational lensing effect. In extreme gravitational fields, the path of light is bent and the flow of time is altered. If an anomalous gravitational lensing effect occurs in a region with signs of time dilation, scientists can hypothesize that a time-stopping boundary may exist there. In addition to scientific research, the phenomenon has given rise to some philosophical musings. For example, the concept of time stopping challenges our understanding of the nature of time. We often think of time as a river flowing forward, and everyone is floating in it. But what if there are places where time actually stops? Would this mean that time is not an absolute being, but can be altered or even frozen by extreme conditions? Furthermore, if time has stopped in certain regions of the universe, does this mean that eternity exists? Would it mean that certain parts of the universe would be preserved in a particular state forever, never to experience change again? This not only makes one think about the physical boundaries of the universe, but also makes us reflect on the boundaries of time, whether time is finite or whether it is just a dimension that we perceive. 10. Cold dark matter distribution boundary. Dark matter is a kind of matter that we cannot directly observe at present. It does not emit or reflect light, nor does it interact electromagnetically with ordinary matter, so we cannot observe it directly with conventional telescopes. Instead, scientists hypothesize about its existence through its gravitational effects. In other words, dark matter is invisible, but it can show its image in the universe by bending spacetime and affecting the motion of galaxies. The hypothesis of dark matter was first proposed in the 1930s when the German astronomer Fritz Zwicky discovered that the mass of clusters of galaxies was far from enough to keep them gravitationally bound, through a study of the movement of galaxy clusters. Today, dark matter is a central topic in cosmology. But here's the most puzzling part: we're still not sure what it is. Scientists have proposed a variety of theories, including supersymmetric particles and weakly interacting massive particles, WIMPs, but none of them have been conclusively proven. Nevertheless, dark matter is crucial to our understanding of the structure and evolution of the universe. The distribution of dark matter is not uniform. By studying different galaxies and clusters of galaxies, scientists have discovered that dark matter is distributed in the universe in a way that resembles large-scale structure, like a giant spider's web, in which the spider's web is a spider's web and the spider's web is a spider's web. The nodes are galaxies and clusters of galaxies, and dark matter, threads, connect these structures. Such a distribution pattern reflects the profound influence of dark matter on the formation and evolution of the large-scale structure of the universe. In particular, by studying the gravitational lensing effect, scientists have been able to see more clearly where dark matter is located in the universe. The gravitational lensing effect is that when light passes through a massive object, such as a cluster of galaxies, the gravitational pull of the object bends the light as if it were passing through a magnifying glass, causing a distortion of the background objects we see. By analyzing how much these rays of light are bent, scientists are able to indirectly project the distribution of dark matter. For example, the famous Milky Way cluster, Abell 1689, is where the distribution of dark matter was revealed through the gravitational lensing effect. By studying this cluster, scientists have found that dark matter accumulates in the center of the cluster, suggesting that its distribution is not only affected by the galaxies, but is also closely related to the large-scale gravitational field. The cold in cold dark matter actually refers to its temperature. Cold dark matter is the opposite of hot dark matter and refers to dark matter particles that are very slow. Why is slow important? Because cold, dark matter particles behave differently from hot dark matter particles in the early universe. Cold dark matter particles are slower, so they play a more important role in the formation of large-scale structures. It doesn't cause the formation of cosmic structures to be blocked because it's going too fast, as hot dark matter does. And it's precisely because of its lower speed of motion that cold dark matter is able to help matter clump together into more tightly packed structures that eventually form galaxies and clusters of galaxies. The distribution of cold and dark matter is closely related to our understanding of the structure of the universe. Modern cosmological models, in particular the lambda CDM model, lambda cold and dark matter model, assume that cold and dark matter is the dominant matter in the evolution of the universe. This model successfully explains the formation process from galaxies to large-scale structures. Cold dark matter acts like an invisible web that helps ordinary matter to gather and form galaxies, clusters of galaxies, and even larger structures. There is also a profound cosmological question at stake here. Is dark matter limited to the extent of our observable universe, or is its distribution beyond that, perhaps even forming additional structural boundaries in places? First, what is the observable universe? Simply put, it is the extent of the universe that we can see through the time constraints imposed by the speed of light. Due to the speed of light, we can only observe the region where light has traveled to Earth in the 1.38 billion years since the Big Bang. Beyond that, we cannot detect light because it has not yet arrived. The distribution of cold dark matter, however, is not theoretically limited by the speed of light propagation. Dark matter influences the structure in the universe through gravitational effects, and as a result, it may be distributed far beyond the boundaries of our observable universe. This means that there may be large amounts of dark matter at the edges of the observable universe, even forming invisible boundaries that we cannot directly perceive. More interestingly, the shape and structure of the universe may also affect our definition of boundary through the distribution of dark matter. Some cosmological models suggest that the universe could be an infinite or extremely large structure, and that our current observable universe is only a small part of it. In this case, the distribution of cold dark matter would not end in the region we can observe, but could be a continuous structure spanning the entire universe. Some theories propose that the distribution of dark matter may help us answer some of the hard questions in cosmology, such as dark energy and the accelerating expansion of the universe. Perhaps dark matter is not only the glue that holds the structure of the universe together, but its distribution may also reveal the deeper structure of the universe. 11. The quantum entanglement limit of the universe. First, a brief review of quantum entanglement. It is a phenomenon in quantum mechanics in which two particles, even if separated by a few light-years, exhibit close contact under certain conditions. When you measure one of the particles, the other particle instantly senses the change, as if they have a way of communicating with each other that goes beyond the norm. Take an example. You and I are holding a special stone. Obviously, I am at the other end of the universe, but when I move in my mind, the stone suddenly changes color. This is the magic of quantum entanglement. It is important to realize that the strangeness of this phenomenon is beyond the intuition of ordinary people. Just as the famous physicist Albert Einstein did not believe in this phenomenon at first, calling it ghostly telepathy. But experiments have proven time and time again that this entanglement is real. One of the most iconic experiments was the 1982 Bell's inequality experiment, conducted by Alan Asper and others, which verified the exact nature of quantum entanglement. Now, let's turn to the boundaries of the universe. The limit of quantum entanglement is in fact closely related to some cutting-edge physical theories. For example, there is a very attractive conjecture called ER equals EPR hypothesis. This hypothesis is put forward by the famous physicist Giles Adam. In short, the hypothesis that there is a deep connection between quantum entanglement and black holes. ER stands for Einstein-Rosen bridge, which is also known as the concept of wormholes. ER stands for the Einstein-Rosen bridge, which we know as the concept of wormholes, while EPR refers to the Einstein-Podolsky-Rosen experiment of quantum entanglement. In short, the ER equals EPR hypothesis proposes the theory that the connection between two entangled quantum particles may be an equivalent to the wormhole structure of a black hole. That is, if you can find the right quantum entanglement, you might be able to travel to the other side of a black hole. This sounds incredible, but it is actually a very serious proposition in modern physics. Based on this hypothesis, a black hole might not just be a gravity vortex, but a portal for information transfer and quantum entanglement. Interestingly, this conjecture has led to a large number of mathematical derivations and theoretical challenges, and many physicists and mathematicians have been fascinated by this problem. For example, does the relationship between wormholes and quantum entanglement mean that we can use quantum entanglement to transmit information without being limited by the scale of the universe? This leads to the central question you ask: is there some kind of limit to quantum entanglement? In traditional physics, we know that information cannot travel beyond the speed of light. That is, whether through electromagnetic waves or any other form of signaling, information cannot travel faster than the speed of light, which is known as the principle of information causality. However, in the world of quantum entanglement, there does not seem to be such a limit. Through quantum entanglement, information can travel instantaneously, at least on the surface. But is there really no limit to this kind of information propagation? Let's go back to the cosmic scale. In the actual universe, is quantum entanglement bound by some global limit? Current physical theories do not give a clear answer. It's like friction between the quantum world and the relativistic world. The two seem to be incompatible. Let us now look at some possible limits. 1. The entropy limit of quantum information. There is a very important concept in information theory called entropy, which describes the uncertainty of a system. In quantum systems, entropy can also be used to describe the degree of quantum entanglement. When the entanglement of a system reaches a certain level, the information capacity of the system may be limited. Simply put, as the level of entanglement of a quantum system increases, the information in the entanglement may become saturated. At this point, no further information can be transmitted. 2. Hawking radiation and the information paradox. Speaking of limits, we have to mention Hawking radiation and the accompanying information paradox. Hawking suggests that black holes can radiate particles, and that this radiation actually leads to a loss of information about the black hole. This raises a profound philosophical and physical dilemma. After a black hole devours information, is that information lost forever? Or can it somehow be recovered from the black hole through quantum entanglement? If the limit of quantum entanglement is the boundary of information loss, what does it mean for the structure of the universe? 3. Decoherence of quantum states. Decoherence is another possible limit. When a quantum state interacts with its environment, it decoheres and loses its quantum properties, becoming a classical system. In other words, quantum entanglement may cease to exist on macroscopic scales due to decoherence. The size of the universe and the complexity of the environment may be a reason for the disappearance of the entanglement effect. Imagine a universe with billions of galaxies, countless particles, and radiation. Such an environment may lead to a rapid deconstruction of quantum entanglement. 4. The structure of space-time and information transfer. If the limit of quantum entanglement is closely related to the space-time structure of the universe, we may need to think about it from a more macroscopic perspective. For example, the model of the universe given by the general theory of relativity, which emphasizes the large-scale curvature of space-time, may affect the propagation efficiency of quantum entanglement to some extent. Space-time itself may impose some kind of limitation on the speed, range, etc. of information transmission. Current science and technology have not been able to answer these questions. While advances in quantum computing and quantum communication have led to a deeper understanding of quantum entanglement, how to apply these studies to phenomena on the scale of the universe remains a great challenge. 12. We often hear about the boundaries of the universe, but these boundaries are not necessarily the visible walls or fringes you might expect. For example, there is a phenomenon called dark flow, which to some extent represents an invisible boundary or an invisible pole. This phenomenon may point to the fact that we can't see what's going on in the world. This phenomenon may point to regions of the universe that we cannot observe, or to some hidden distribution of massive mass. In short, it is a kind of cosmic boundary that we cannot fully understand for the time being. In 2008, scientists made a serendipitous discovery that changed some of our views of the universe. The researchers found that in deep space there were clusters of galaxies that seemed to be moving in an unusual way, and that all of them seemed to be moving in the same direction, much faster than expected. This phenomenon is completely inexplicable by existing cosmological models. Normally, the motion of galaxy clusters is driven by the expansion of the universe, i.e., the aftermath of the Big Bang, but the direction of motion of these clusters doesn't quite fit our current understanding. Not only are these clusters of galaxies shifted in a certain direction, but this shift is so large that it exceeds the speed that should be caused by the expansion of the universe. Astronomers call this phenomenon a dark current. Interestingly, the direction of the dark current does not seem to be limited to our observable universe, or rather, it points to a region that we cannot directly observe. First of all, it should be clear that the dark current is not a flow of matter, as we often say. For example, the flow of water or air is generated by the movement of matter, while the dark current refers to an anomaly in the movement of clusters of galaxies. This phenomenon is not due to gravitational forces between galaxies, nor is it due to an object that exerts a significant influence between them. So how do dark flows actually form? There are several possibilities, and one of the most popular theories is that the dark current may originate in a region of the universe that we cannot observe. This region might contain an extremely large structure of matter, or, alternatively, hide some sort of distribution of mass, perhaps even a giant object that is undetectable by our current scientific tools. Simply put, the dark currents could be pointing to some unknown source of mass whose gravitational action is having an effect on the matter in our observable universe. If this theory is true, then it may be pointing to a region that is currently beyond our ability to directly observe by any available means. It could even be at the edge of the universe, or have been pulled by some undetectable force in the very early stages of its formation after the Big Bang. The direction of this speculation may point to another dimension of the universe, a spatial structure beyond what we can see with our eyes. So why is the dark current phenomenon called a boundary? We usually think of the boundary of the universe as an endpoint that is beyond our reach, or perhaps a boundary or a limit. However, the boundary of the dark current is different. It is not a physical boundary that we can see directly through the telescope, but a boundary of force that we can perceive through the phenomenon. In other words, the boundary of the dark current could be the distribution of some kind of giant mass in the universe, somewhere far away, far beyond the reach of our current observational tools. This boundary doesn't mean that you can see it directly, but rather that there is a mysterious region outside the range of our observations, where some kind of huge gravitational source, which cannot be understood in the usual way, is pulling some of the matter in the universe, and in the sense, the dark current becomes a mysterious region outside the range of our observations. In this sense, the dark current is the invisible boundary of the universe. It points to a region of the universe that is temporarily out of our reach, or to the heart of one of the unsolved mysteries of the universe. Do dark currents have anything to do with dark matter, you may ask? The answer is that the phenomenon of dark current may be indirectly related to dark matter. Dark matter is another of the great unsolved mysteries of cosmology. It does not emit light or other forms of radiation like ordinary matter, and therefore cannot be directly observed. However, the existence of dark matter can be indirectly hypothesized through its gravitational influence on visible matter. The appearance of the dark current phenomenon hints at the possibility of the existence of certain undiscovered matter in the universe, possibly related to the distribution of dark matter. Perhaps the unknown region to which the dark current points is a large-scale gathering place of dark matter. It could be a huge object that is not directly visible, or a massive cloud of dark matter whose gravitational pull causes the anomalous motion we observe. Thus, not only do dark currents give us a sense of the boundaries of the universe, but they also give us more speculation and associations with dark matter. Perhaps this mysterious direction is the source of dark matter or other unknown substances. The phenomenon of dark current undoubtedly provides astronomers with a new research direction. Scientists have begun to try to uncover the truth of this phenomenon through more precise observation means and theoretical models. For example, using more powerful astronomical telescopes and detectors, astronomers have begun to track clusters of galaxies at greater distances in an attempt to detect their trajectories and to further confirm the existence and nature of the dark current by comparing the speeds of motion in different regions. On the other hand, scientists are also trying to reproduce the dark current phenomenon in computer simulations. By simulating the large-scale structure and gravitational effects of the universe, astronomers hope to find more evidence that dark currents are not just an accidental phenomenon, but a manifestation of some kind of deep-seated forces in the universe. For example, some researchers have suggested that if dark flows are associated with hidden massive mass distributions, then such mass distributions should have pronounced gravitational effects on surrounding objects under certain circumstances, potentially affecting the trajectories of galaxies. 13. The high temperature limit. When we talk about the boundaries of the universe, what is the first thing that comes to mind? Is it the distant galaxies or the never-ending darkness of space? But if the perspective to put more to think about the temperature, this seemingly simple concept, the boundaries of the universe is not just our eyes in the distant sky, but a deeper, more mysterious field. In this realm, when the temperature reaches a certain limit, even the laws of physics begin to collapse. This limit is called the Planck temperature. Before we formally explore Planck's temperature, a little background is in order. How do scientists define the limit temperature of the universe? The concept of Planck's temperature originated with a giant of physics, Max Planck. Planck was a German physicist who played a crucial role in the quantum theory breakthroughs of the early 20th century. In order to understand the origin of Planck's temperature, we need to understand what Planck units are. Planck units are a system of fundamental units based on natural constants. That is, these units are not set by man, but are determined by the natural laws of the universe. For example, Planck length, Planck time, and Planck mass are examples of units whose values are calculated from four fundamental constants: the speed of light, c, Planck's constant, h, the gravitational constant, g, and the vacuum dielectric constant, epsilon. Planck's temperature is one of these constants, and it can be regarded as the limiting temperature of a universe. Formulaically, the Planck temperature is about 1.416 times 10 to the 32nd power Kelvin. So how hot is the Planck temperature? In everyday life, the temperature of a flame is about 1,000 degrees Celsius. The surface temperature of the sun is about 5,500 degrees Celsius, and the surface temperature of even the hottest stars is only a few million degrees. The Planck temperature, on the other hand, is much hotter than these. It's so unimaginably high that the concept of heat as we know it every day no longer applies. Its temperature is so enormous that it exceeds the states of matter that we can currently observe and understand. Interestingly, the extremes of the Planck temperature take us into an almost incomprehensible realm. At this temperature, the effects of quantum gravity and quantum physics become extraordinarily powerful. More specifically, this temperature is so high that the laws of modern physics begin to break down. Think about it, if you heat matter to such a temperature, it has enough energy that it can even cause the structure of spacetime to change. It's not just the effects of heat that come with this temperature, even the concepts of space and time could become blurred. Scientists speculate that at this temperature, spacetime itself would begin to undergo quantum changes that cannot be described by our current physical framework. As an example, we now use classical physics to understand the temperature and energy of objects. However, the Planck temperature invalidates these conventional ways of understanding. Cosmologists imagine that in the first few seconds of the universe's existence, the so-called Big Bang moment, the temperature approached or reached the Planck temperature. At that time, everything in the universe was in an extremely strange state. All the particles were so densely packed together that even the line between gravity and quantum effects was blurred. That said, one can't help but think of black holes, and these extreme objects also characterize Planck temperatures in some way. While Planck temperatures may seem intimidating, their existence is quite abstract. Today, scientists cannot create experimental environments that reach such high temperatures. Even the most powerful particle gas pedals cannot approach the Planck temperature limit. Therefore, the Planck temperature can only serve as a theoretical upper limit, which tells us where the limits of physics and the universe lie. Back to our daily life, the concept of temperature is usually understood based on the macroscopic behavior of matter. When we see a handful of matches burning or feel sunlight pouring down on our bodies, we are actually perceiving the thermal motion of matter. The limit of Planck's temperature, however, is no longer based on the motion of matter itself, but on the workings of the most fundamental forces, particles, and even structures of spacetime in the universe. At this level, temperature becomes an almost untouchable abstraction. You may have heard of black holes, one of the most mysterious and powerful objects in the universe. So what do black holes have to do with Planck temperature? Interestingly, the extreme conditions of black holes alone have certain overlaps with Planck temperatures. In particular, the introduction of the Hawking radiation theory has dramatically changed our understanding of black holes. Hawking radiation is a theoretical phenomenon that describes the process by which a black hole emits radiation outward under certain conditions. This radiation originates from the quantum effect that when pairs of imaginary particles appear near the event horizon of a black hole, one of the particles may be sucked into the black hole and the other escapes into outer space. According to Hawking's projections, the black hole will gradually lose mass due to this radiation and may eventually evaporate. So where does Hawking's radiation fit in with Planck's temperature? The temperature of a black hole is related to its mass, and when the mass of a black hole becomes extremely small, its temperature approaches the Planck temperature. In fact, some researchers believe that the temperature of a miniature black hole may approach this limit. For a more intuitive understanding, it can be envisioned that as the mass of a black hole gets smaller, it gets warmer and may eventually approach the Planck temperature. The earliest theoretical prediction of the Planck temperature comes from the Big Bang theory. According to current cosmological opinion, the universe began expanding from an incredibly hot, dense blob at some point about 13.8 billion years ago. Scientists believe that the temperature of the universe used to be close to the Planck temperature during the first seconds of its birth. This period is known as the Planck era, and it's special because the extreme conditions of this period make it impossible to accurately describe with our current physical theories. Imagine, every particle and every force in the universe was in a huge energy field, and the boundaries between space-time, matter, and forces became extremely blurred. This period, scientists call quantum gravity era, because in such extreme conditions, quantum mechanics and gravity, two seemingly independent forces, have to work together. It can be said that Planck's temperature represents not only the limit of temperature, it also symbolizes a limit of our understanding of the universe, a wall that we cannot cross. When we try to understand the Planck temperature, we are not just talking about a physical quantity. Its limiting nature reminds us that the rules of the universe are not just what we can see and touch, but that there is a side to them that is out of reach. The boundaries that science has explored have often led to philosophical revelations as well. Some scientists and philosophers have even suggested that such limits may mean that we will never fully understand the nature of the universe. Perhaps the universe itself has a set upper limit, and when physical quantities such as temperature and energy reach this limit, the entire structure of the universe becomes unpredictable and no longer fits into our current scientific framework. 14. Antimatter-matter boundaries. #antimatter-matter boundaries. The loss and mysterious disappearance at the beginning of the universe. We know that almost all of the matter in the universe is made up of matter, the stars, planets, and even ourselves. We know that almost everything in the universe is made of matter, the stars we see every day, the planets, even ourselves. However, if you go back to the very beginning of the universe, things may not be so simple. In the early stages of the universe, matter and antimatter existed almost simultaneously in the same amounts and under the same conditions. However, now that the universe is made almost entirely of matter, antimatter has disappeared almost without a trace, or rather, it has virtually disappeared from our range of observation. We know that there is a fatal property between antimatter and matter. They will annihilate each other when they collide, releasing a great deal of energy. Matter and antimatter must have existed side by side at that time, so what caused antimatter to disappear? Is there some kind of cosmic boundary that we have not yet uncovered that separates antimatter from matter? This is a seemingly simple, but in fact extremely complex question of physics. Let's start from the beginning of the universe and try to understand the causes and consequences of this mystery, and see how the relationship between antimatter and matter has become a puzzling boundary phenomenon in the universe. Before we go any further, it is important to briefly review what antimatter is. We know that matter is made up of atoms, which in turn are made up of protons, neutrons, and electrons. Simply put, protons are positively charged and electrons are negatively charged. Antimatter is the mirror image of matter, which is made up of antiparticles. These antiparticles have charges and other properties that are opposite to those of ordinary particles. For example, the antiproton in antimatter is negatively charged, the opposite of an ordinary proton, and the antielectron, often called a positron, is positively charged, the opposite of an ordinary electron. Theoretically, antimatter and matter are perfectly symmetrical, and if they meet, an annihilation reaction occurs, converting the mass of both into energy, releasing a huge amount of energy according to Einstein's mass-energy equation, E equals mc squared. This is why antimatter is often regarded as a reservoir of energy. The energy released by the annihilation reaction between antimatter and matter can be extremely powerful. In the early stages of the Big Bang, scientists hypothesized that matter and antimatter were created almost in pairs. There were theoretically the same amount of both, and they should have produced a large amount of radiation after colliding and annihilating each other in the early universe. According to our current physical theories, matter and antimatter should have coexisted within seconds of the Big Bang and maintained some sort of equilibrium through a constant process of annihilation and creation. However, today's universe is composed almost entirely of matter, and traces of antimatter are so rare that they are almost impossible to detect. This imbalance is known as the matter-antimatter asymmetry, baryon asymmetry, and is one of the deepest unsolved mysteries in cosmology. If we look back at the first few minutes of the universe's existence, according to the standard Big Bang model, matter and antimatter should have coexisted in almost equal amounts, and as the universe expanded and cooled, they continued to annihilate, creating the remaining matter. This is what we call particle-antiparticle symmetry breaking. However, according to existing observations and calculations, there should theoretically be a very small difference that would give matter a slight edge, and this small difference would eventually lead to the almost purely material universe that we see today. So why is matter and antimatter asymmetric? This has been a central topic of debate and research among cosmologists for a long time. Theoretically, the following mechanisms may explain this phenomenon. 1. CP symmetry breaking. CP symmetry refers to whether or not the laws of physics remain unchanged under the charge conjugation, C, and the inversion of the US symmetry, P. Theoretically, if there is a slight CP symmetry breaking between particles and antiparticles in the early stages of the universe, it could lead to a tiny asymmetry between matter and antimatter. This tiny asymmetry was amplified over time and eventually formed the matter-dominated universe we see today. 2. Early stages of cosmic expansion. The expansion of the universe after the Big Bang was an extremely rapid process. The theory of the upsurge pointed out that the universe experienced a violent expansion in the initial moments, which led to a drastic change in the temperature and density in the initial universe, and thus may have led to a small difference in the distribution of matter and antimatter. This process of cosmic expansion may have frozen this difference, resulting in the matter-dominated universe of today. 3. Introduction of new physics. Some scientists have suggested that the matter-antimatter asymmetry may be a manifestation of new physics that goes beyond the explanations of the existing standard model. Perhaps there is some particle or force that we have not yet discovered that may have caused the isolation or disappearance of antimatter from the universe. To varying degrees, these explanations all attempt to answer the question, where did the antimatter in the universe go? Why is it not on a par with matter? In a sense, the absence of antimatter reveals an invisible boundary of the universe. This boundary is not a boundary in physical space, but an asymmetric distribution of matter and antimatter in the universe, or it may be a physical mechanism that has not yet been discovered by us, resulting in some kind of separation or isolation between antimatter and matter. It is a mysterious boundary between the existence and disappearance of antimatter. Let's imagine this scenario. In a very short period of time after the Big Bang, matter and antimatter coexisted in almost equal quantities, but at some mysterious moment, matter and antimatter began to annihilate. And after the annihilation of the remaining matter in a slightly superior quantity, this small deviation ultimately determines the composition of the entire universe. This disappearance itself acts as an invisible boundary line in the universe, marking the transition from the early matter-antimatter symmetry to the current matter-dominated universe. This phenomenon is not only mysterious, but also intriguing. If antimatter was once so abundant, why has it disappeared in the history of the universe? Is it isolated by some force beyond our comprehension? Or is it still hidden somewhere beyond our reach? Just because we can't directly track antimatter right now doesn't mean scientists have given up trying to find it. Through in-depth study of the cosmic background radiation, detection of interstellar particles, and even experiments in particle gas pedals, scientists are still working to unravel the mystery of antimatter. 15. Large-scale cosmic inhomogeneity boundaries. First, a brief review of the cosmological principle. This principle says that from a macroscopic point of view, the universe is homogeneous and isotropic on large scales. That is, the universe has roughly the same distribution of matter and radiation when viewed in any direction. You can think of it as an oversized ocean of galaxies and clusters of galaxies, and no matter where you stand, you will see a similar view. This is the basic starting point for our current understanding of the universe. This principle originated in the early 20th century, when astronomers and physicists, including Albert Einstein and Friedman, proposed, based on the theory of general relativity, that the universe should behave uniformly on large scales, with no special centers or boundaries. Observational data at the time seemed to support this theory, because from any telescope on our planet, it seemed that all parts of the universe were similar, and galaxies did not show any obvious regularities. But as science and technology continued to advance, especially since the second half of the 20th century, and as astronomical observations improved, we realized that this uniformity assumption seemed to be a bit of a problem, and that the universe, at least on larger scales, didn't seem to be so neat. There is a kind of non-uniformity in the distribution of matter, and this non-uniformity itself may, in places, reach levels of complexity that we cannot imagine. Let's dig a little deeper and see how these inhomogeneities manifest themselves. Through modern astronomical observations, we have discovered that the universe is not uniform like a flat piece of jello, but rather like a giant web of galaxies, clusters of galaxies, and larger structures. This large-scale structure is called the cosmic web. In these structures, clusters of galaxies and galaxies form the nodes of the network, which are separated by vast, almost substance-free voids, called cosmic voids. This structure does not have the same layout everywhere, and it is highly hierarchical and directional. In some regions, galaxies and galaxy clusters are densely distributed, while in others, galaxies are virtually absent, creating vast regions of vacuum. This inhomogeneity is apparent on large scales. And as we delve deeper into these large-scale structures, we find that the further away we look, the more pronounced the inhomogeneity becomes. One of the best-known pieces of evidence for this has come through observations of large-scale structure, LSS. These studies show that the distribution of matter in the universe is not uniform on very large scales. By mapping the distribution of galaxies, scientists have found that the distribution of galaxies is like a giant web, with clusters of galaxies and galaxies forming the filaments that connect the massive voids. This is reminiscent of the structure of a spider's web. Voids are like gaps in a grid, and clusters of galaxies are like intersections of the grid. This structure ranges from millions of light-years on the smallest scales to billions of light-years on the largest scales, presenting a hierarchy that challenges the assumption of a homogeneous universe. For example, by studying the Wolf-Taguchi spectrum, LSS, scientists have identified the apparent inhomogeneity in the large-scale structure of the universe. While on smaller scales, such as the scale of individual galaxies, we can still assume that the distribution of matter is homogeneous. When we look at wider scales, this homogeneity begins to collapse and is replaced by a complex picture of voids, filamentary structures, and nodes. Okay, now that we know that the universe is a complex mesh on large scales, what exactly is the large-scale inhomogeneity boundary? We can discuss this question from two perspectives. 1. Boundary of large-scale structure. This boundary is not a clear wall or boundary, but a kind of distribution on this boundary is not a clear wall or line, but a gradual change in distribution. In some regions, the density of matter is very high and clusters of galaxies are very dense, while in other regions there is almost nothing. This difference causes the cosmic web of different regions to become dense and compact in some places and loose and empty in others. For example, between clusters of galaxies, you can see several millions of light-years long empty regions where there is almost no matter. 2. Anomalous regions of matter distribution. The more mysterious part is whether there is some sort of beyond the visible or unobserved limit to this inhomogeneity. As you may know, there doesn't seem to be any directly visible matter outside the universe that we can observe, but that doesn't mean that there isn't a universe out there. Farther out, there may be regions of undetectable matter or voids, which in some cases may form some kind of limiting inhomogeneity. Some physicists have even suggested that some regions of the universe may have extreme inhomogeneities that we can't imagine due to distortions in spacetime, possibly due to some unknown physical effects. Speaking of the large-scale inhomogeneity of the universe, it is important to mention the early evolution of the universe. For millions of years after the Big Bang, the matter in the universe was not evenly distributed. Over time, matter began to gather, forming the galaxies, galaxy clusters, and voids we see today. Tiny density fluctuations in the early universe, which gradually amplified with the expansion of the universe, eventually formed large-scale structures of matter. In fact, the cosmic mesh structure we see today is the result of the accumulation of these density fluctuations on large scales. These fluctuations can be traced back to fluctuations in the cosmic microwave background, CMB, radiation. When scientists observed the CMB through the Planck satellite, they discovered that tiny temperature fluctuations in the early universe were the source of these large-scale structures. These fluctuations, along with the expansion of the universe and the evolution of matter, gradually developed into the massive galaxy clusters and voids we see today. Although this uneven distribution of matter may seem random, there is a key factor behind it: dark matter. Dark matter influences the aggregation of ordinary matter through gravitational forces and is a key driving force in the formation of the large-scale structure of the universe. The gravitational pull of dark matter pulls matter toward it, resulting in the distribution of galaxy clusters and voids on large scales. Think of it as the invisible glue that holds ordinary matter together in a mesh. Without dark matter, the distribution of matter in the universe would be more uniform, and the formation of galaxies and clusters of galaxies would be affected. There is not really a clear answer to the question about the large-scale cosmic inhomogeneity boundary. It represents a kind of ambiguity in the boundary of the universe. In our observation range, the distribution of matter shows obvious inhomogeneity, and galaxy clusters and voids form the cosmic web. But does it represent some kind of ultimate boundary? Or is it possible that the distribution of matter in the universe has undergone extreme variations in some parts of the universe, creating anomalous regions that we cannot observe? 16. The Fermi Paradox Boundary. The Fermi Paradox, named after the physicist Enrico Fermi, is centered on the question: if the universe is so big, why haven't we discovered the existence of extraterrestrial civilizations? If alien civilizations exist and they have sufficient technological capabilities, logical reasoning dictates that they should have expanded to all corners of the galaxy over their long history, or even traveled interstellarly, leaving behind some sort of sign that we can detect, whether it's the detection of their signals or the discovery of certain high-tech objects, buildings, even the remains of a spaceship. But the truth is, we don't have any such signs so far. What's even more interesting is that Fermi joked at the time, "Where did they go?" This statement is both a question and a profound reflection on this phenomenon. From a scientific point of view, the core problem of Fermi's paradox can be roughly divided into several parts. 1. The vastness of the universe. The universe is not only vast, but also filled with countless galaxies and planets. In our galaxy alone, there are between 100 and 400 billion stars, which may be surrounded by Earth-like planets. Moreover, the universe is much older than the Earth, having been nearly 14 billion years old. Considering these conditions, alien civilizations should theoretically have sprung up and expanded as far as we can detect long ago. 2. Timescale. Even if alien civilizations develop very slowly, assuming they have sufficient technology and resources, millions or even tens of millions of years should be more than enough for civilization expansion. If alien civilizations really existed, they could have long ago entered our observation range through interstellar travel, information dissemination, or other means. 3. Technological capabilities, as envisioned by modern science and technology. Once extraterrestrial civilizations have the capability of interstellar travel or are able to build probes that can explore long periods of time and long distances, they can easily travel across interstellar space in the Milky Way galaxy, searching for resources, spreading knowledge, and even coming into contact with a young civilization such as ours. But despite such strong theoretical support and reasonable speculation, the fact remains that we have not found any signs of anything like this so far. So, what exactly is the reason why alien civilizations have not visited or even left any traces? At this point, we need to think from multiple angles. Perhaps this question is not only about the existence of extraterrestrial civilizations, but also involves some physical and sociological boundary issues. The first thing we must consider is the scale and distance of the universe. Even if extraterrestrial civilizations exist, they are probably on the other side of the universe, very far away from us. The distance in the universe can be measured in light years, and even if we travel at the speed of light, it will take thousands of years, or even longer, to reach a distance of several thousand, or even tens of thousands of light years. Therefore, alien civilizations, if they exist at all, may be in a place that is inaccessible through our current technologies and methods, or their signals may have disappeared, vanishing into the depths of space and time millions or thousands of years ago. In other words, the distances of the universe itself constitute a huge physical boundary that makes crossing these distances almost impossible. For example, if an extraterrestrial civilization is located on the other side of the Milky Way, the signals they send may have decayed along the way or may not reach us. Another very interesting point to think about is the life cycle of an alien civilization. Our human civilization is just at the beginning of interstellar travel. We've just launched probes to start exploring other planets and small bodies in our solar system, and there are even some private companies planning to launch humans to Mars. For extraterrestrial civilizations, will their existence and development last as long as ours into the interstellar age? According to Carl Sagan, alien civilizations, if they exist at all, probably disappeared millions of years ago. The existence of civilizations tends to be short-lived, especially highly technological civilizations, and once technology advances to a certain level, they may become extinct due to self-destruction, depletion of resources, wars, and so on. As a result, alien civilizations may have very short life cycles, and this leads to the fact that they do not have the opportunity to leave lasting traces in the universe. For example, civilizations on Earth have had two possible civilization-destroying events. The first was the threat of a large-scale nuclear war, and the second was the possible irreversible consequences of climate change. Both of these factors could cause civilizations to disappear in a very short period of time on a cosmic scale. Thus, even if extraterrestrial civilizations were capable of interstellar travel, they would probably disappear before they had a chance to reach us. 3. Technological borders. Besides distance and time, another possible explanation for our invisible signals is technological borders. Perhaps alien civilizations possess technologies that we cannot understand or receive. They may use a method of signaling that is completely undetectable to us, or they may have higher dimensional communication technologies that are completely black box to us. For example, extraterrestrial civilizations may be transmitting information through quantum communication, FTL communication, or other means that we have not yet discovered, making their presence undetectable to us. 4. Social or cultural boundaries. Another explanation is that the social or cultural structure of an alien civilization may have some kind of self-limiting boundaries. Imagine that an alien civilization may have ethical, moral, or social structures that we cannot understand. They may be aware of the existence of other civilizations, but choose not to interfere or even make contact with us due to some sort of galactic empire non-interventionist principle. Perhaps their very existence is a form of invisibility. As David Brin mentions in Being, there may be some kind of tacit, invisible boundary between civilizations. As David Brin mentions in his book, Being, there may be some kind of tacit, invisible boundaries between civilizations, i.e., at certain stages of technological development. Alien civilizations would choose to avoid contact with other civilizations to prevent possible dangers or unintended consequences. 5. Another pessimistic explanation for the possibility of loneliness is that we may be the only civilization in the universe. This idea is a bit heavy-handed, but it cannot be ruled out. The history of our universe is much longer than the history of mankind, and the conditions for the origin of civilizations may be so complex that chance may have determined whether or not a civilization was born, survived, and developed. Perhaps alien civilizations have not come as far as we have, and much of the universe remains barren and empty. The Fermi paradox is indeed a thought-provoking question, and the boundaries it involves are not only limited to whether we can find evidence of extraterrestrial civilizations, but more profoundly, it makes us reflect on the limitations of the universe, of time, of civilization, and even of ourselves. Perhaps there will never be a definitive answer to the Fermi paradox, but its formulation has undoubtedly stimulated our infinite curiosity about the universe. Well, that's it for this installment. Likes and comments are welcome. Thanks for watching.